All right. So, of course, we can't have relativity talks, especially special relativity, without the twin paradox and the Lorentz contraction ladder paradox. But with this one, we're going to revisit the twin paradox. So, on their 21st birthday, one twin gets on a moving sidewalk which carries her out to star X at speed 4/5c. Her twin brother stays home. When the traveling twin gets to star X, she immediately jumps onto the returning moving sidewalk and comes back to Earth, again at speed 4/5 c. She arrives on her 39th birthday, as determined by her watch. A. How old is her twin brother? B. How far away is star X? Give your answer in light years. Call the outbound sidewalk system S bar and the inbound one S tilde. The Earth system is S. Again, the bar tilde prime goes to the moving thing. All three systems choose their coordinates and set their master clocks such that X equal X bar equal X tilde equals 0 and T equal T bar T tilde equals 0 at the moment of departure. All right. Now, we're going to have to ask a couple more questions, and let's see what we get. So part C, what are the coordinates X and T of the jump from the outbound to the inbound sidewalk in S bar? What are the coordinates X bar T bar of the jump in S bar? And what are the coordinates X tilde T tilde of the jump in S tilde? Okay. Again, be careful with your notation and which ones you want to use. So part F, if the traveling twin wants her watch to agree with the clock in S bar, or S tilde, I can't see, how must she reset it immediately? How must she reset it after the jump? What does her watch then read when she gets home? G, if the traveling twin is asked a question, how old is your brother right now? What is the correct reply? 1. Just before she makes the jump. 2. Just after she makes the jump. Okay? H. How many Earth years does the return trip take? Add this to answer 2 from G to determine how old she expected him to be at their reunion. Compare your answer to A. Holy moly, we got a lot of stuff going on here, so let's take it one step at a time. We have everything set up that we need to. Now it's just a matter of applying definitions correctly. So, in our solution, since we know running clocks move slow by a factor of gamma, where we have V over C, so we're just left with 4/5 squared, that comes out to 5/3 once we multiply by the reciprocal. So since 18 years had elapsed on the moving clock, we have 5/3 times 18 because 39 minus 21 is 18. And this gives us 30 years elapsed by the stationary clock. So she is now 21 plus 30 equals 51 years old. That part's not too bad. We just have to be very careful with what we do with the rest of these things. So now in part B, on the Earth clock, it took 30 divided by 2, so 15 years to get there at the speed 4/5 c. So if that's the case, we have D equal VT, so V being 4 divided by 5 times C times 15 years gives us 12 light years. Okay. That being said, we're assuming that both of them are symmetric, so we got to be careful. So in S, the Earth system, we have T equals 15 years and X equals 12 light years. So meaning that it took 15 years to get to star X at a distance of 12 light years away. Now, in the S-bound or S-bar or the outbound sidewalk, we have, again, we were told that 18 years elapsed in the total trip. So S T bar is just 18 divided by 2, since we're doing halfway out there and halfway back at the same velocity. So we get 18 divided by 2 is 9. And again, we're not, with the fact that we have moving in x, our x is still 0. Reason why is shown here. If that's the case, we have x bar equal gamma times x minus vt, but we see that x is equal to vt, so they cancel to 0. Again, we can also think of it in terms of Lorentz contraction, but nonetheless, let's continue. Now in part C, note that the s tilde is the direction opposite, is in the direction opposite, so is v. Okay, so we just have to flip the signs, and that's what I highlighted in red. So x tilde, we have to add these two things, so we get 24 light years times 5/3, so we're actually 40 light years distance away. Now t bar, again according to the reference frame that we're using, now or t tilde is the same thing, except now we have to 4/3 or 5/3 times 123 over 5 years, so we get 41 years. Holy moly, that's a lot. Alright, so moving forward, and we got to be careful moving into the later parts of this for obvious reasons. So for part F, set her clock ahead 32 years, so from 9 to 30, or from 9 to 41. That's our translation from t bar to t tilde. The return trip takes 9 years, moving time, so her clock will now read 50 years at her arrival. Okay, so we set it forward from 9 to 41. Since the return time takes 9, we have 41 plus 9 gives us 50. And so this is 5/3 times 30, which is precisely what you would have calculated if the stay at home had been the traveler for 30 years of his own time. So we're comparing, everything looks right, so we're good. Now in part G, the one for answer 1, we have t equal 9 years, x equals 0. So what is t? Send it through, we get 5.4 years in the bar system. And he started at age 21, so in this system he's 26.4 years old. Similarly, with what we just discovered for transitioning it to the tilde system, we have t is equal to 41, send that through with the Lorentz factor, and we get 24.6 years. And if he started at 21, 24.6 years, right at the start of the tilde system, gives us a 45.6-year-old twin brother. So in H then, it will take another 5.4 years of Earth time for the return. So when she gets back, she will say her twin's age is 45.6 plus 5.1 is 41 years old, which is what we found in A. Roughly speaking, of course. So we have to be careful with our rounding, but things are looking right, and that's what we need. So we'll see you at the next one.